Among the most profound enigmas in science is this: was there anything before the universe itself? The Big Bang Theory proposes that our cosmos took shape nearly 13.8 billion years ago, erupting from an unbelievably hot and dense origin into the immense expanse we observe now. This genesis unfolded with an explosive growth of space, cooling temperatures, and the emergence of the earliest atomic particles. Yet, what came before this cosmic dawn remains cloaked in mystery. It may be that time and space themselves sprang into existence with the Big Bang, forging a boundary that our physical laws cannot cross. Nevertheless, human curiosity drives us to search for answers. For generations, both scientists and philosophers have wondered if the Big Bang truly marked the beginning, or if it was merely a single act within a much grander cosmic saga. Today, we embark on a journey to uncover what current science reveals about the origin of time. We will delve into fresh discoveries that deepen our knowledge of the early universe, and consider audacious theories that stretch beyond the Big Bang. To begin, our most trusted scientific models indicate that the Big Bang stands as time's starting point, the birth of the universe as we recognize it. In one fleeting moment, every shred of space, time, energy, and matter burst forth from a singularity of infinite density. During the very first sliver of a second, the universe experienced breathtaking inflation, expanding at speeds surpassing that of light within an ever-stretching fabric of space. This dramatic episode set the groundwork for all that followed. A single second after this event, the universe was a searing, opaque stew of subatomic particles. Mere minutes later, the first light chemical elements came into existence through primordial nucleosynthesis. The young cosmos was so intensely hot and dense that atoms could not yet assemble, and light, constantly scattered by free electrons, could travel only short distances. For several 100,000 years, the universe remained shrouded in a foggy, impenetrable haze. As time marched on and expansion continued, cooling allowed profound changes. Fast forward 380,000 years after the Big Bang, the universe had finally cooled enough for electrons and nuclei to unite, forming neutral atoms. This epoch, known as recombination, transformed everything. Once electrons were captured by atoms, light could at last roam freely through space. The primordial fog lifted, and illumination swept across the cosmos. This ancient light still envelops us, arriving as a faint glow from every direction, stretched over billions of years of expansion into the microwave spectrum. We call this the cosmic microwave background, or CMB, a literal snapshot of the universe in its infancy. By studying the CMB, researchers can glimpse the cosmos as it appeared when it was just 380,000 years old, a mere infant compared to its 13.8 billion year existence. This is the oldest light we are able to observe, a relic image of the Big Bang's fireball. Since the 1960s, scientists have measured the cosmic microwave background with ever greater precision, using satellites and telescopes. The CMB preserves an astonishing trove of information. Its modeled pattern of tiny temperature fluctuations is anything but random. It preserves the seeds of the cosmic web that would later emerge. Slightly denser areas in this early map eventually collapsed under the grip of gravity, giving rise to galaxies and clusters. In essence, the CMB serves as a blueprint for the universe's future structure, mapping the peaks and valleys in original matter distribution. It also helps decode the geometry and overall character of the cosmos. Decades of careful study have revealed a surprising truth. Ordinary matter, the stars, planets, and all life, accounts for only about 5% of everything in the universe. The remainder is far more enigmatic. Approximately 27% is dark matter, while nearly 68% takes the form of dark energy, according to measurements gleaned from the cosmic microwave background. Groundbreaking findings continue to reshape our understanding of the cosmos. In March of 2025, a team working with the Atacama Cosmology Telescope at Princeton University unveiled the sharpest images yet of the cosmic microwave background, providing the most vivid snapshots of the universe in its infancy. These new visuals, boasting 5 times greater resolution than the previous all-sky map produced by the Planck satellite, also captured the polarization of this ancient radiation. By analyzing the orientation of these primordial light waves, scientists can discern both the movement of light and matter across various regions of the youthful universe. "We once could only map where things were," says Dr. Suzanne Staggs, who leads the ACT project. "Now we can also observe how everything is moving." These finely detailed images reveal minute variations in both the density and speed of the original cosmic gas, offering insights into the intricate landscape of those first hills and valleys. Such data allow researchers to tackle long-held mysteries about how our universe progressed from a state of elegant simplicity to its dazzling present-day complexity. It is nothing short of awe-inspiring. By studying light that has journeyed for over 13 billion years, we are able to peer at the universe as it existed mere hours after its cosmic birth. If the cosmic microwave background represents the lingering thermal glow of the universe's earliest days, what events followed in the cosmic timeline? Once recombination occurred, the cosmos slipped into what astronomers call the Dark Ages. With the primordial fog dissipated, the background light slowly faded, and for a time, no new sources of illumination emerged. Stars had yet to appear. This long darkness was finally pierced when the very first stars, likely forming between 100 million and 200 million years after the Big Bang, sprang to life. These primal suns, known as population 3 stars, were probably enormous, short-lived giants that began to light up the newborn cosmos, gathering within nascent galactic clouds and ushering in the era of galaxy formation. Astronomers refer to this transformative epoch as the cosmic dawn, the moment when the first starlight dispelled cosmic darkness. Today, thanks to immensely powerful telescopes, we are starting to witness glimpses of the cosmic dawn firsthand. The James Webb Space Telescope, which was launched in 2021, is designed to capture the faint infrared glow from extremely remote galaxies. Because radiation from the early universe has been stretched, redshifted, into the infrared, the Webb telescope is ideally equipped to detect it. In just its initial years of use, the James Webb Space Telescope has broken every record, revealing galaxies that existed merely a few 100 million years after the Big Bang. One such cosmic find, playfully named MAMZ14, was in 2025 hailed as the most distant galaxy ever observed. The light from this remarkable object began its journey just 280 million years after the Big Bang. In effect, we are witnessing this galaxy as it was when the universe was only about 2% of its present age. That ancient light traveled nearly 13.5 billion years to finally reach the James Webb sensitive instruments. Since beginning operations in 2022, the James Webb Space Telescope has uncovered far more luminous ancient galaxies than astronomers had anticipated. This unexpected bounty has sent waves of excitement through the scientific community and has prompted fundamental questions about how galaxies took shape within the first 500 million years of cosmic history. Every newly discovered high redshift galaxy provides another clue, helping us unravel how the grand structure of the universe emerged in its earliest epochs. Take MAMZ14, for instance. Analysis suggests that this galaxy was undergoing a swift period of star formation at the moment of its detection. Its chemical makeup, especially its high abundance of nitrogen relative to carbon, bears a striking resemblance to the composition of the oldest globular clusters in our own Milky Way. This finding hints that the process of star formation in this ancient era may have been quite different from later times. These astonishing discoveries compel astronomers to rethink how quickly the universe's first tiny fluctuations, visible in the cosmic microwave background, could give rise to entire galaxies. How could such colossal radiant galaxies have assembled with such incredible speed? Are stars and galaxies emerging at a pace that surpasses what our simulations forecast? Or could it be that our grasp of the universe's timeline is still incomplete? As cutting-edge observatories begin their work, we anticipate glimpsing even closer to the dawn of time, potentially catching sight of celestial bodies formed during the epoch of the universe's very first stars. Yet, regardless of how advanced our telescopes become, they will never uncover what transpired before the Big Bang. For insights into that primordial era, we must rely on theoretical models. Over billions of years, under gravity's relentless pull, matter within the cosmos assembled into a sprawling intergalactic web. Galaxies are far from evenly scattered. Instead, they align along filaments and broad sheets, separated by vast emptiness. This intricate network can be traced back to subtle fluctuations imprinted on the cosmic microwave background. By and large, our models rooted in the Big Bang theory and an ever-expanding universe suffused with dark matter indicate that there exists a maximum threshold for the size of cosmic structures. A fundamental concept, the cosmological principle, stands at the heart of modern cosmology. It holds that on truly grand scales, the universe should appear largely uniform, with no outsized clusters or pronounced features dominating any given region. In essence, when we consider volumes spanning hundreds of millions of light-years, every sector of the cosmos ought to look more or less alike. According to prevailing theory, the largest coherent formations should top out at around 1 billion light-years across. This is precisely why astronomers were astonished to identify structures that vastly exceed these theoretical limits. In the year 2024, scientists uncovered a monumental ring-like arrangement of galaxies and galaxy clusters, christened the Big Ring. This feature stretches to an immense 1.3 billion light-years in diameter and encircles a distance of roughly 4 billion light-years. The light we now observe from this formation began its journey toward us some 9.2 billion years ago, meaning we see it as it once was in the distant past. Remarkably, this cosmic ring lies near another gargantuan formation known as the Giant Arc, which itself extends a staggering 3.3 billion light-years. To put these mind-boggling dimensions into context, our own Milky Way supercluster spans a mere 500 million light-years across. Both the Big Ring and the Giant Arc are veritable titans amidst the universe's tapestry. Delving deeper, recent analyses suggest that the Big Ring might not be a ring after all. It could, in fact, be a vast spiral or corkscrew-like structure winding through space. If it were somehow visible to the naked eye, which it is not due to its overwhelming distance and faintness, one scientist noted it would appear about 15 times wider than the full moon in our night sky. Such a feature is beyond the explanatory reach of our most robust cosmological theories. The size and distinctive organization of the Big Ring make it difficult to reconcile with baryon acoustic oscillations, the pressure waves that shaped the early universe. While these could lead to large-scale distributions of galaxies, the resulting structures should be roughly spherical shells, not elongated rings, and certainly not on such an epic scale. Should the data continue to hold, it may imply that our assumptions regarding the universe's large-scale uniformity are due for revision. Neither of these two megastructures fits comfortably within our current cosmological framework, observes Alexia Lopez, the astronomer credited with their discovery. Their immense proportions and peculiar forms are undoubtedly trying to tell us something fundamental about the cosmos, but what? One explanation is that these extraordinary assemblies are mere statistical anomalies, random concentrations that, by chance, emerged larger than expected. However, the odds of finding not just one, but several such colossal structures, including the Sloan Great Wall, the South Pole Wall, and the enormous quasar groups, grow increasingly slim. Some intriguing proposals suggest that these vast patterns may point to new physics or previously unknown aspects of the universe's formative conditions. Perhaps some exotic process during the universe's infancy brought forth such megastructures, challenging the boundaries of conventional inflationary cosmology. Consider, for instance, the notion of cosmic strings. These are theoretical, unimaginably slender imperfections in the fabric of spacetime, thought to be remnants from immediately after the Big Bang. If such entities truly exist, They could have shaped how matter spread across the universe on truly colossal scales. While the existence of these objects remains speculative, they exemplify the fresh kinds of physics researchers are willing to entertain in order to account for such puzzling phenomena. Taking things a step further, the illustrious physicist Sir Roger Penrose offered an even more daring hypothesis. He contends that such cosmic features might be indicators of a pre-Big Bang universe. In his framework, called conformal cyclic cosmology, the Big Bang was not the origin, but a bridge between cosmic epochs. If correct, then echoes from a former universe could be imprinted within our own. Penrose even went as far as suggesting that circular marks spotted in the cosmic microwave background may be remnants of gravitational waves, unleashed as a previous universe met its end. Although a majority of cosmologists remain unconvinced, the presence of such strange possibilities compels us to admit that our grasp of early universe physics may be incomplete. Let us recap our current understanding. The Big Bang signifies the onset of the universe's expansion, and during its first several billion years, gravity gradually slowed this outward motion. However, in 1998, scientists were stunned by a discovery. The expansion was not decelerating, but speeding up. An unknown force, eventually named dark energy, was pushing the cosmos outward, outmatching gravity on the grandest scales. To this day, dark energy stands as one of cosmology's most profound riddles. We know it constitutes roughly 68% of all that exists, behaving like a sort of anti-gravity that pries galaxies apart. For many years, the most straightforward explanation has been to consider dark energy as a cosmological constant, an immutable property of space, perhaps tied to the energy of the vacuum itself. In our leading theoretical framework, the so-called lambda cold dark matter model, with lambda symbolizing dark energy, this force is presumed to be steady across time, making the universe's expansion accelerate at an ever-increasing rate indefinitely. Yet, data from recent years has begun to challenge this view. Evidence collected by the Dark Energy Spectroscopic Instrument, known as DESI, which has mapped countless galaxies and quasars, suggests that dark energy's sway may have changed over cosmic history. At the beginning of 2025, scientists sifting through 3 years' worth of DESI observations unveiled new hints that dark energy has waned over billions of years. Put differently, instead of providing an unwavering shove, the repulsive power of dark energy may be slowly subsiding. As Dr. Arjun Day of the National Science Foundation's Noir Lab remarked, the DESI findings offer tantalizing signs of a shifting dark energy. Should this prove accurate, it would transform our cosmic narrative. It might indicate that the universe's accelerated growth will not last forever. Indeed, as one researcher observed, whatever is driving the universe's expansion could be losing potency. This development prompts enormous questions about the ultimate destiny of the cosmos. Will the acceleration eventually ease or halt entirely? Is it possible that gravity could ultimately reassert itself, causing the expansion to slow or even reverse? The answers remain elusive, but it is evident that the old assumption of an unchanging dark energy is now being questioned. Much like the puzzle of dark energy, another unseen yet vital component of the universe is under intense examination: dark matter. Though invisible except through its gravitational pull, dark matter is thought to provide the underlying structure for galaxies and clusters, playing a pivotal part in simulations of cosmic structure formation. Without it, explaining the rapid emergence of galaxies in the early universe becomes exceedingly difficult. Despite many decades spent in search of it, no dark matter particle has ever been observed directly, and its true essence continues to elude us. This ongoing mystery has inspired some scientists to consider radical alternatives to the standard Big Bang model, scenarios where neither dark matter nor dark energy is required at all. This audacious idea was introduced by Dr. Richard Liu, a professor of physics, introduced a revolutionary concept in the year 2025 that challenges the long-held notion of a solitary Big Bang. In Liu's framework, the universe's growth and the appearance of vast cosmic formations emerge not from a single cataclysm, but from a succession of mini-bangs, or fleeting singularities that unfold one after another. Rather than envisioning everything as the aftermath of a lone explosion, with continuous acceleration propelled by dark energy, Liu posits that the cosmos might have experienced several surges, bursts of energy and matter injected at various epochs, effectively taking the places of both dark matter and dark energy. Each time such a burst occurs, matter and energy are released throughout the universe in a uniform manner, and the singularity then vanishes as swiftly as it appeared. These eruptions are so rare and brief that direct observation is nearly impossible. They resemble cosmic flashes, each leaving behind a subtle alteration in expansion rates and sparking the birth of new galactic structures. In the intervals between these bursts, the universe drifts onward, requiring no enigmatic dark energy to fill empty space. Liu's hypothesis stands out, as it resurrects elements from the old steady-state theories, which proposed ongoing matter creation, but now in a form that does not breach the conservation of energy. Liu emphasizes that, in contrast to the classic steady-state model, discarded because it assumed matter could be created continually from nothing, thereby defying established physics, his transitional singularities flicker in and out of existence so quickly that they sidestep these violations. For an infinitely short span, a burst infuses mass and energy everywhere and is then gone. Remarkably, this notion does not break the laws of physics as we know them, though it certainly stretches them to their limits. These transient singularities would generate a kind of negative pressure within the universe's fabric, much like the effect attributed to dark energy. Essentially, each burst could spark a phase of accelerated growth, offering a solution to the dark energy mystery for its era while also planting the seeds for galaxies, addressing the puzzle of dark matter. The paper suggests that the Big Bang itself might have been merely the initial event, a precursor in a series of such eruptions, the first in a cosmic sequence. Where the standard cosmological model sees one singular act of creation, Liu's vision allows for many. This marks a profound shift from traditional ideas, but for now, it remains highly speculative. How could we determine whether this idea reflects reality? Scientists propose searching for telltale signatures in observational data. For example, one could look for barely perceptible jumps in the relationship between redshifts and distances of remote galaxies. If the universe did experience multiple bursts of expansion, then distant objects might not align in the smooth curve predicted by models with unvarying dark energy. Instead, there could be subtle discontinuities tied to these ancient events. Whether or not this specific theory holds up, its very existence underscores an important truth. The Big Bang model, despite its enormous achievements, still contains mysteries that may require thinking beyond the notion of a single beginning. This leads to a broader question. What if the Big Bang was not the ultimate origin? Contemporary cosmology entertains such possibilities. For instance, Roger Penrose's vision of a cyclic universe suggests that our Big Bang is just the most recent in an endless series, each universe rising from the ashes of its predecessor. In this scenario, at an inconceivably remote future time, when the universe has expanded beyond recognition and all matter has faded away, it might enter an almost vacant state, eerily reminiscent of the conditions that heralded the first Big Bang. At that juncture, a new era could commence. This elegant attempt to unite the end with the beginning remains a fascinating idea, though it has yet to achieve mainstream acceptance. Curiously, Penrose asserted that he had identified concentric rings within the cosmic microwave background, interpreting them as echoes of gravitational disturbances from eras that came before our Big Bang. Nevertheless, the majority of specialists remain skeptical of these claims. The notion of a universe cycling through endless phases is far from novel. Ancient thinkers once imagined perpetual cycles, and even certain contemporary theories, such as the asiperiodic universe concept, where higher dimensional brains collide, propose a bounce scenario instead of a solitary origin. These models offer one possible response to the question of what existed beforehand. There was something. Perhaps another cosmos. Perhaps another loop of existence. Another perspective posits that time itself was born alongside the Big Bang, suggesting that asking what occurred before is a meaningless question. It is akin to asking what lies beyond the North Pole. For many years, this was the prevailing view derived from general relativity. At time equals 0, our mathematical descriptions fail, leading to the conclusion that time simply did not exist prior to that instant. Yet, the field of quantum physics challenges these boundaries. Certain quantum gravity theories, including loop quantum cosmology, suggest the Big Bang may have been a grand rebound, a previous universe collapsing and then springing forth into the one we observe now. Within these frameworks, time flows continuously through the bounce. Thus, there was a before, a universe preceding the bounce, and perhaps remnants of it linger in our current universe. This is a fascinating possibility, the Big Bang as a transformation, not an emergence from absolute nothingness. If dark energy is indeed evolving and could someday reverse, as findings from the DESI experiment indicate, we might envision our cosmos contracting in the far future, culminating in a colossal crunch that sparks another explosive birth. Of course, such ideas remain speculative, yet they highlight that the boundary dividing before and after the Big Bang is a subject of active inquiry and rigorous debate. The evidence available to us today outlines a universe remarkably well characterized by Big Bang cosmology, but it also brims with enigmas that put this model to the test. For now, what happened before the Big Bang is an open mystery. It sits at the very edge of scientific exploration, where data is sparse and imagination must blend with strict mathematics. Still, as demonstrated, scientific progress continues to shed light on the earliest epochs of the cosmos. Will direct proof of a pre-Big Bang reality ever come to light? Perhaps not in a straightforward way, but indirect hints could one day surface. If our universe is merely one episode in a grand cycle, future scrutiny of the cosmic microwave background or the arrangement of galaxies might uncover faint signatures left by a former cycle. Should the Big Bang prove to be but one in a sequence of eruptions, we could eventually detect fossilized remnants of those fleeting phenomena in our observations. Or perhaps, a future unified theory of quantum gravity will enable us to infer the prior state that ignited our universe. Which of these possibilities do you find the most convincing?